Hi class, welcome to ECS 36B. This is the sixth lecture. We're going to talk about a topic called shadow objects. Shadow objects is one of the interesting ideal application of both inheritance and polymorphism. And I hope you still remember that we went over a basic concept about inheritance. We look at cases like a single inheritance. We also look at things like virtual functions and protected members or member function, which enable us to put things together. We can start building very interesting application based on those language constructs. So today we're going to see another interesting thing we can do. It's called shadow objects. So number one, let's first talk about what is a shadow object. So assuming that we have this scenario here, the real object is actually running on a different machine. Maybe it's somewhere else, may not be even in Davis, that this object is really monitoring the air quality, coronavirus, or something else that's actually physically located with some activity monitor or sensor in different parts of the world. While we are at home or at UC Davis, we like to remotely access the information and interact with those objects as shown in this picture. And what you really want this to happen is that you want to develop an application as if the machine is, not the machine, the object is right next to you on your machine. Just like when you did homework assignment number 2, you started seeing transaction object, person object, and also GPS object and other objects. They're being created on your laptop or on CSIF machine. It's kind of convenient that you have all the object around you that you can simply write a function call and to interact with those objects. Things getting a little bit inconvenient when those objects are really being decentralized. Some of the objects are in Africa, some of the objects may be in South Pole. Some of the objects are actually in the most busiest street in New York City, and some of the objects may be in the middle of the ocean. And therefore, how do we conveniently handling such kind of situation is what we want to implement as a concept of shadow object. In this picture that you're seeing right now, this is in fact the scenario for your homework assignment number 3. So you have a real object on a different locality, which is on Cyrus, for example. And then you have another instance of object, which this object we call a shadow object. Is representing the same object but is located nearby on your machine, even within the same application. Okay, so now your application, when they try to invoke one of the member function, for example, get distance, like what you have done in your homework assignment number 2. So when you perform this function, get distance, because your local object, the gray circle on the left, is a shadow of the real object. So it actually take your message, take your call, but instead of process locally, try to do the distance calculation, it actually forward this request to the real object on cyrus.cs.ucdavis.edu, which they really have 2 GPS locations. They can actually calculate the distance between those two, and then they will send the result back to your shadow object and then feedback to your local application. So your application, as if it is interacting with the object in a remote location, as it is locally communicating, and then it can get a result. We have a total transparent situation for your application. So this is the idea of shadow object. Let me just summarize that you have a local representation of a remote object, even though that you really want to interact with that remote object, you only locally interact with the local shadow. And that will help you as a wrapper, as a proxy for you to do the real job. So that's the idea of a shadow object. So the concept of shadow object is very simple. You can have two objects, you have a multiple object, you can have a shadow forwarded to another shadow may be a shadow for a lot of different regions, and then they will forward, try to find the real object for you to do. So the concept is very simple, but the application is really broad and really powerful. I mean, for example, now I show you a case. You can do distributed programming. You don't have to program just for the local object. You can actually connect the world together and doing distributed programming. Part of your program will be running on your local machine, but part of your program may be running on your refrigerator. And part of the program may be running on a monitor about the temperature or CO2 level in North Pole. And you can do distributed programming with this concept of shadow object. It's much easier for you to develop a large-scale program. The second thing is really interesting as well is abstraction about how you can manage a lot of distributed or remote resources. So you can think about today we're talking about Internet of Things or IoT, and you have billions of sensors everywhere around the world. And the thing is that each of the sensors, you can think about the container or hosting a small number of objects that actually represent what's going on around the world. And those objects can provide information with your local application. So instead of for you to worry about where are those each object, what you can do is you can actually create lots of shadow represent those IoT sensor that you're mostly interested. And then you're just locally interact with the local abstraction about that part of the world. And then that software or that mechanism called shadow object will make sure that whatever you're interacting locally will actually get to the right object remotely to be able to complete the work correctly. And also, this imply also you can checking for any kind of dynamics as we are really separate from the local to the remote copy. So while you are sitting here and looking at your screen and running some program, the temperature in North Pole might have changed slightly. Or maybe some of the coronavirus situation in Manhattan have update. And therefore, those update is being done remotely. And the thing is that your local copy need to do the right thing and such that those significant change will be reflected to your local copy, so you will get the newest result for you to do the right things in that case. And of course, you can also think about the object as an entity that will move. I mean, just using the example of person. A person is an object, or it represents a bunch of objects that's actually maybe there's some interesting application for social network. And the thing is that when you're moving, locally, I'm still seeing I have a lot of shadow objects represent each of the person that I like to interact with. But when they move to one location to the other, I don't have to worry about their movement. Because why? All I care is a local copy, I call shadow, of the entity I would like to interact with. But when that particular person moves, the shadow object will tracking how they move and then will send the message to the new locality of a person when they move, say, from New York to Sydney. And then that locality will follow that, and such that even though you're still dealing with the locality, dealing with the local shadow object, but the locality has been captured by the shadow object mechanism, and such that you don't need to worry about all these changes, and you can still have develop your application. So I cannot emphasize enough that the mechanism of shadow object, in fact, dominating our world. If you think about all the application on the web application, peer-to-peer application, there's a lot of application, or search engine, that's another one, social network. They all, in some sense, utilize the concept of shadow object. And so if you learn how to do shadow object, you can actually develop a lot of interesting, exciting application for yourself. Okay. All right. So so this class, we're going to talk about shadow object and how to do the implementation. We're not just talk about the concept, but we need to get our hand dirty and see how we can really do it. So we're going to look at, basically the implementation of a shadow object is try to provide some objects, which this object can be implemented by C++, JSON, Java, Python, or anything. And how they might be utilized, the shadow object, to communicating with each other. So we're talking about a communicating object in the distributed world. Well, however, that this particular lecture, because now we're focused on C++, I'm going to particularly looking at how we can accomplish this shadow object in the context of C++ programming language. And particularly, we're going to utilize both inheritance and polymorphism and see how they can handle that as well. Okay. Okay, so the first thing I like to talk about is a concept maybe new to most of you. It's called remote procedure call. So remote procedure call is trying to accomplish the following. So in this slide, the top part is a very simple example of a function call. There's function called foo, and somebody actually called that function foo, and then you have somewhere else have the foo, the implementation or the definition of foo that will be called. So it's a caller and callee situation. All right, so this is a regular procedure call. You're calling a function locally on your machine, and most likely is on the same program or same, what we call the same process that you call the other function. So this is called the regular function call. But what we really want to do in the concept of remote procedure call, when you say remote procedure, it means that we're going to do this remotely. So we essentially now split the caller and the callee. So the caller, which is the one who wants to call the function foo, is on the left, while the callee is actually on the right. So this separation is very useful because when you can separate this into two different parts, which it imply is that I can put one part of that to be run SQ on one side of the world, where the other part I can actually just let it run on the other corner. And then in the middle you have communication. It looks like as if you're doing the upper part, is doing a local procedure call. And then in fact you're doing the scenario in the bottom of this slide, which is the left side is calling the right side, while left and right, they are actually on totally different corner of this internet. Okay, so this is a convenient, and you can imagine this is very useful, that we can essentially worry about a local call scenario, but we can actually break down and distribute the logic and computation to different parts of the world for a variety of reasons. Some of them I already explained to you when we talk about shadow object. Okay. All right. So in order to implement this idea, remote procedure call, your homework assignment number 3, some of you already start working on, it's called RPC, that you have to solve two problems. In fact, any remote procedure call, this two problems you must find a way. You must find a way to deal with. Number one, you have to locate the entry points. So when I split the caller and callee in two different parts of the world, I mean, I have to let the caller know where is a callee and how to access a particular port number on the callee and which function that I actually want to call that's being reside on that callee on the right hand side. So some of you during the weekend try to deal with simultaneously homework 1, homework 2, part 1 and part 2. And one of the students actually messed up the port number. So it's very interesting. I cannot explain that why he's working on this part of the homework, he will get that error message. And it turned out that that particular student used the wrong port number. So the student thought he's working on this part of the homework, but it's actually the server handling the request is totally a different part of the homework, and therefore you got the error message totally unexplainable. And similarly here, the first question is that we have to know where's the entry point, which IP address I should get to, which port number, which function, and those kind of things. So that's the first thing we need to address when you want to implement a remote procedure call. The second part you want to deal with is that when you make a function call, it's not just call, but you also have argument. You have some data you need to transfer from the caller to the callee. And also the callee, after finish the result, they need to have a way to transfer back to the caller. And this might sound very natural in a local computation environment. This is by far very, very tedious when you want to deal with a remote location. And some of this might not even be implemented in the same programming language. And some of this are not running on the same platform for a long period of time. Just try to make it interoperable between a Unix machine and a Windows machine already create lots of challenge you must deal with associated just represent the data. Okay, so this the second part is how do you actually handle the data format for argument and the result. Okay, for example, let's actually using this simple program to see what the remote procedure call looks like. So this is a program some of you have already downloaded from the tar file of homework assignment number 3. You can see that this is a program for homework 3 client.cpp. And this program, by the way, is very short. It's a very short program, and it basically creates two objects called shadow fly. By the way, I will explain to you the difference between flight and shadow fly. So shadow fly is the shadow object version of the class flight. Okay, so what I have here is I just create two shadow objects, shadow F3, shadow fly F3, shadow fly F2, and then you can see what I did is I just call this function, for example, get distance. F2.getDistance, meaning that I'm calling the function getDistance, but this function is actually being executed at a remote location, and which I will demonstrate to you a bit later. But this is the idea that we want to call this function remotely. It's not just about locating where it is, but also about the argument as well as the return value. So in this case, you can see that I fortunately get distance. I don't need to provide any argument, so there's nothing I need to worry about, but I do need to worry about the return value. The return value is going to return a double, in which I need to encode that such that it will be able to give me the correct result. Okay. And to handle that, to look for the identity. So the first question we want to have, the first challenge we have is trying to find the entry point where it is. So if you look at the top part of the slide, in this new lecture I introduce a new class. This class is called core. It's core object, and the core object is a very unique object. Its purpose of designing this core object is try to facilitate the implementation of the shadow object. So sometimes I design a new object such that I will be able to capture a way to implement a distributed programming platform. So this core object, in fact, any object you want to implement in a way of doing shadow object or remote procedure call, you're going to have a core object. And the core object, you can see that it has four major attributes: host URL, owner, virtual ID, and then class ID and object ID. So this actually provides me the entry point to the object I really want. Because where's the object I first have to know is host URL. I know where is the HTTP address, so I can actually go there to look for the object that I would like to interact with remotely. And the owner VSID is that because they might be multiple students or multiple people who host their object there, and I want to actually interact with the one that I really want to interact with. And I don't want to interact with a random people who give me a random information. So that's why you have that owner VSID. And the third one is called class ID, which is which object class that you're dealing with. And then, for example, the class could be this: I want to interact with the transaction class. And then within that transaction class, you might have multiple objects, and which object you like to interact with, and that's object ID. So you have four attributes: host URL, owner VSID, and class ID and object ID. It will uniquely identify the object that you need to deal with. And then you can actually make remote procedure call to invoke that particular object in the right way. Okay, so now you probably got some rough idea about what we like to accomplish with the mechanism shadow object. And also you learn conceptually about what the remote procedure call try to accomplish. They both try to accomplish the same scenario, which one piece of software, they want to interact with something locally, but the real interaction is something or somewhere in the other part of the internet. Okay? So now we're going to talk a little bit more detail about the implementation. How is remote procedure call is done, and how can we extend the idea of remote procedure call to cover the idea of a shadow object. So remote procedure call was developed in the 1980s by Sun Microsystems. Currently is a part of Oracle. And at that time, they developed the software they call the RPC Jam. It basically take a specification of the interface. So this is the I would say the very fruitful area for object-oriented paradigm developed. So everything is driven by interface. And this interface at that time is called XDR. XDR stands for external data representation. It's a way to allow different parts of the computer or different platform, they would be able to exchange information under the same format. And in the modern day, that, I mean, XDR, by the way, is still a lot of real systems are still using XDR. But there is alternative to XDR right now. It's called JSON. So that's why for homework assignment number 3, you're trying to install a package called JSON RPC. So it's the RPC based on JSON instead of based on XDR. So when I developed the RPC program the first time around 1989, I was actually using XDR RPC, and then using RPC Gen, and then I would be able to get these things to work. But right now we should be using JSON RPC because number one, it's simpler, and it's actually much nicer to connect with the JSON world as well. Okay. So let me tell you that what is the JSON RPC is doing. So what JSON RPC is doing is that you use JSON format, you specify an interface, and that file in your part 1 of homework assignment number 3 is called spec.json. So spec.json is actually trying to specify that interface. And then you're going to use this program called JSON RPC stub. So what the program is doing is taking that interface file, spec.json, and it will produce 2 files. In fact, depending on whether you're using RPC Gen or JSON RPC stub, sometimes it produces 2 files, sometimes it produces 4 files. But ultimately, what you like to have is have a 4 file. One is called client.h, client.cpp, the name you can change. And the other side is server.h and server.cpp. And what it needs to happen is that you use client.h and server.h as it is, because the .h file specifies the data format. It specifies what data you're going to transfer and what function call you're going to communicate between these 2 functions. If you look at the output generated by JSON RPC stub, to look at the .h file, you will see a lot of virtual function. I mean, basically virtual function is so useful, and you will see inheritance there as well. So I'm not going to spoil your fun. Okay, you're going to take a look at that. But there's another 2 files also needed to complete this picture, and one side is called client.cpp, one side is called server.cpp. So client.cpp and server.cpp has some kind of template to work with the .h file, but they are not complete. Just like homework assignment number 2, part 2, you're receiving some file which is partially finished. And therefore, the client CPP and server CPP need to connect to some of the code in the application of this remote procedure call. Let me give you an example. If I want to write a remote procedure call to read the distance from the other sensor on the server side, then the client CPP need to connect the caller part, the program that want to call that get distance function. So that's going to be included in the client.cpp. And where the server.cpp need to connect from that code to the real object. Because if you don't do this 2 stitching point on client.cpp and server.cpp, you are not connecting the object together. You want to connect the client with the server, so you need to do that stitching. And that stitching is not being specified by the interface. The interface only say what data need to be transferred. It doesn't say which function I need to call. And therefore, that stitching, you have to do that separately. So once you've done this stitching, then you will be able to put together and such that the client.cpp will be compiled into executable, and such that the server.cpp will compile and running, and then the client CPP will actually talk to them and get the data. Just similar to what you have done in homework assignment number 1 and number 2, you both connecting with the service on Cyrus. Okay, so that's a very quick overview about remote procedure call. So remote procedure call, you have to specify the interface. you use the stub or RPC gen to generate those files. Then you modify the CPP file together the rest of your system. Then you can actually conduct a remote procedure call. All right. Well, however, that remote procedure call itself is not enough to realize the remote object or shadow object, because RPC just tell you that, hey, I want to call a remote function. But in a object-oriented setting, you not only need to know that this is a function I need to call, but I also need to know which object I need to access for this function. Because as a member function, you could have 10 millions of objects out there. How do I know which one of those 10 million I need to connecting with? And therefore, you need to have something extra be built on top of RPC, and you can complete this connection. It's not just a remote procedure call, but it's a remote shadow object that you can have one object or one application talk to the other object. And in fact, that's the part 2 of your homework assignment number 3 that we would like you to exercise. Of course, we gave you a lot of example and help, and hopefully you can develop yourself a truly object-oriented remote procedure call. All right. All right, so what we need to have is that we need to find out where are the objects. So that's why the core object come in. The core object gives you this 4 parameter or 4 attribute: URL, VSID, class, and object. So the URL tell you where this server is, and the VSID tell you that this is application specific, tell you that what is the credential or what is the identifier you need to know in order to know who actually owns those objects. And then within the object space, I need to know whether I'm dealing with the right class or I'm dealing with a particular object. So this 4 attributes put together help us to identify where I can find the right object. So as I mentioned before, that this is the core object which we'll be using for the rest of this lecture. Okay, so with this idea of a remote object, it's quite interesting that you have the core object. Now I'm actually showing you a program, which is similar to the program I showed you earlier. It's a client program that it has 2 objects being created, that both of them are shadow fly. So shadow fly is a shadow version of the object fly, which is really hosted somewhere else. But what's interesting about this example I want to tell you is that with this mechanism, you can do things really powerful. And for example, the F3, the first fly object I try to interact with, the object is actually on Cyrus, which is 169.237.6.102, and belong to one particular person, that somebody with VSID 9876. While the second object, which is actually running on a different machine, you can be a local host, it could be somewhere in South Pole, and it has a different VSID as well. So essentially what we're showing you is that by fairly short amount of programming, I can connect different parts of the world into the same space, even though they're in different URL, they're in different user, and I can integrate this information and do something very useful to put this information together. Okay, so now let's see how to do this implementation. So this is from your homework assignment number 2. You have 2 classes. I'm just simplifying the problem a little bit. So one class is person class, one class is transaction class. Okay, so we have this 2 classes from homework assignment number 2. So now I'm going to introduce a new class called flight. And this is a real class. We haven't talked about shadow flight. We talk about the flight. So this is the first time we're going to use the inheritance. So you can see the definition. The class flight is inherited from transaction. So flight is a transaction. It's a subclass of the transaction. And I define a bunch of new things that specifically to fly. So transaction is a general activity, while flight is a specialization out of that general transaction concept. So that's a very proper use of the mechanism inheritance. All right. So one thing I would like you to just pay attention a little bit, because I modified this a little bit. So now I move the get distance function to number one to the fly. Number two, now I make that a virtual function. So essentially, this is exactly the same as your homework assignment number 2, part 2, except I move the get distance from transaction to the fly. The second thing I'm doing here is I make a virtual function. So if you remember, the virtual function is something which potentially we can show different behavior even though it's the same function, the same kind of object, which I will show you later how I use this virtual function mechanism to accomplish the idea of a shadow object. Okay, so now I have this 3 class, and now we're so far so good, and this is extended slightly from your homework assignment number 2. So now I'm going to start to have this core object to bring in. So I create another object called core object. The core object has the 4 attributes as I mentioned, and also I want to make sure the core object is on the root of the major classes that I want to implement a shadow object, because I said that in order for me to implement shadow object, I have to have this core object. So in my implementation, which is related to the tar file I shipped to you, the core object is a parent class of both person and transaction, and is ancestor of the fly as well. So I show you a piece of code. You can see now I modified the class transaction. You will see that in the tar file. So transaction is inherit from core, and similarly person inherit from core as well. Okay, so now this is the core object is over here. So now we have core object, person, transaction, and fly. Now we can actually already implement the server. So remember, we use the spec.json, or in homework assignment number 3 is actually ECF36B homework 3.json, that we can produce the server.h and server.cpp. So now we want to implement this function called getDistance. So under the class flight, so what my implementation of getDistance, which is exactly your implementation of getDistance for your homework assignment number 2. So I get this geoDataSource distance function, and whenever I see a shadow object send me a request about calculating the distance, I'm going to call geoDataSource distance. And so now remember, I'm on the server side. So somebody remote try to call me, and then I will actually call the function. And so with the core, person, transaction, and fly, I already can implement the core object. Sorry, the get distance function. Okay, so just to let you know that what's happening in the server.cpp. So I put it on the yellow small corner on the like a skeleton about the logic about the server.cpp I need to implement. Of course, it needs to include server.h. It needs to include transaction.h. Those definition file it has to include. But the second part is really locate the right object. I want to find whether the request is for the same class, the same object. I need to identify what is the object I really need to call. And then once I get the right object, then I will just call get distance for that object. Okay, so that's what I talk about. I I let the RPC to take care of the parameter, and then I basically just make sure that I find the right object for you to call. So on the server side, this picture is sufficient. Okay, so now let's look at the client side. So in the client side, you can see that I'm pulling out the program again, but now I'm actually using different highlight somewhat differently. So there's still those two shadow flight, and those two are the HW3 client.cpp. It's very simple. The homework 3 is very simple. But the tricky part is that now I have this on the top. Now you see that I'm actually defining the new class called shadow flight. So shadow flight is a subclass of flight. So now you see I'm using inheritance to differentiate between a regular project and the shadow object. And within this shadow fly object, which I just introduced, the constructor, in fact, is very simple. If you remember the fly's constructor, fly actually took a lot of parameter, like the GPS, like who is the passenger, who's the ticket number, and which is airline. But have you seen that the shadow fly, I only have 4 string without all this number or GPS or whatever. Why? Because shadow object is not a real object. Shadow object only need to get those information about locality, which is URL, VSID, class ID, and object ID. The only thing I need is that I need to access to the object in a remote location, and I don't have any content about that object. This is, by the way, this is go extreme into the concept of encapsulation, because I'm actually interact with the object. I don't have to own the detail. And with this information, I already can do a lot. Okay, so that's the shadow flight, which has that constructor, which is only construct the core object part of this object. So just remind you, shadow object inherit from flight. Fly inherit from transaction, and transaction inherit from core object. So okay, it's a whole line that you have that over here. Okay, the second thing I want to emphasize on this slide is that now I have get distance as well. And look at this as a virtual function. Remember, the fly has a get distance virtual function, and shadow fly also have a get distance shadow object, virtual function. Okay, so that's basically I introduce this shadow fly, and then I can just using this 2 line, you can see that I can call, and then I can actually first I can initialize with those 4 parameter, URL, VSID, and then the class name and the object ID, and then I can just call it and then get a result print out. Very simple. So now we're looking at the other part of the story, which this part of the code is generated by the JSON RPC stub. Okay, so this piece of code is belong to HW3 client.h, which you shouldn't change. That this code will be there as it is. So if you go back to the previous slide, that it's not the previous slide. I reverse over there a little bit. Okay, so now I want to tell you that in this particular code, which is class HW3 client, they basically also use inheritance, but inherits from JSON RPC colon client. Okay, it inherits certain kind of property. But what's interesting in this particular code is that it generates a code function called ECF36B HW3, and it took a bunch of parameter, and it actually prepare all the information related to the JSON, such as the action, argument, class ID, host URL, object ID, and the owner VSID, those information. After they prepare all this information, they will just call this method, this function and then send the whole JSON to the other side. So this piece of code was generated. It's actually based on the interface that we provide in the JSON file. And then it will then handle the transition from the client side to the remote and then get the result and send it back. And you have to look at the next slide, the previous slide, I skipped a little bit. You look at this slide, is the implementation of the get distance of the Shadowfly version. So in the Shadowfly version, the get distance is not calling the geodata source version. What it does is actually doing the plumbing to connect to the code that's actually being generated by the JSON RPC stub. So what it does is that you can see that number one, it tried to just create the HTTP client to set up a JSON connection with a remote location. And then it basically just called this function called myclient.ec36b_hw3 and put in the parameter like we just did. And now you can see that I'm actually using, by the way, this piece of code is we have to develop in the Shadowfly .cpp, but in the middle you can see there are 4 parameters there: class ID, host URL, object ID, and the owner VSID. You might notice that the order is a little bit different than the order I presented earlier. The reason I present this order is that when I develop the JSON file, I actually include this 4 in the original order. But somehow the JSON RPC stub program, when they generate the function, like I showed you earlier in the HW3 client.h, that function takes the parameter that the generated code follow a different order. So actually, I look at the code, decide that this is the correct order for me to integrate with the code. Okay, so similarly, when I call this, and then at the end, the result is good, it's giving back to my V, which is my JSON value, and then my V is going to return the real value to the caller. Okay. Okay, so this is what we have right now. Now we have a core on the top of the class hierarchy. Both person and transaction are inherited from core, and fly inherits from transaction, and now we have a Shadowfly that's actually inherited from fly as well. And the server part, you just need to use a fly because server is not a shadow object. You don't need to deal with the shadow fly, while the client need to interact with the shadow fly. And the very critical point here is the virtual function get distance. You can see that that function is actually in the flight, but also in the shadow fly. It's the same function, but the behavior is totally different. So depending on how you create the object, it doesn't mean how you casting the object. It's really depending on how you create the object. If you create the object as a flight, then you're going to call the flight version of get distance, which you're going to call geodata source version of the GPS calculation. But if you're creating the object using Shadowfly as a class, then you're going to invoke the get distance from the code I just showed you, which is not going to have a local data. It's just connect to the JSON RPC stub generated code and to connect to the remote to grab the data back to you. Okay, so that's the picture we're talking about today. Now I just want to pause a little bit to recap what we have. So we're now using inheritance. So we make sure that we build the right class, especially we want to introduce the core object to allow us to put this 4 attribute for us to recognize which object is where, which one we want to talk to. And the second thing is that we really cleverly utilize the idea of virtual function, and such that depending on how you create this object, that it will determine whether this is a local copy or this is a remote shadow copy that I need to actually invoke the shadow object protocol. Okay? All right, so now we're going to do some real work. So now you have the concept. It's always good for you to download the tar file that, as specified in homework assignment number 3, you should download the file. I updated on Monday, April 20th. Okay, you should take a look at the newest version. When you take a look, download the file, you use the tar ZXVF, you're going to get the following file, which is I show you on the screen. You have, of course, you have core.hcpp, person H and person CPP, transaction H, transaction CPP, and also you have shadowfly.h and shadowfly.cpp. Those are the class definition and their implementation. But I also give you a example version of HW3 server.cpp and HW3 client.cpp, as I already presented to you earlier in this particular lecture. And I give you the JSON file which enable this interaction between the client and the server. And of course, I give you the make file. So this is a complete package that if you just type in make, you should be able to get everything to work, assuming you have done homework assignment number 3, part 1 successfully. And this, you can just do a make, then you can get this one to work, okay? All right, so this file, you have all of this. So now you can get it compiled. The first step I want to show you is that if you, when you type in make, the first wave of things that will happen is the blue thing. The blue link means that the ECF36B HW3.json is going to generate using the JSON RPC stub program. It's going to generate HW3 server.h and HW3 client.h. So I didn't even include that in the package because I think anything that could be regenerated, I don't want to include. You just type the command, it will come back to you. And also, I want to tell you that you're not supposed to change this to file. Okay, that's the blue part. And now the green link is interesting. The green link represents the dependency relationship in the compiler. So that we capture in the make file. For example, in order to compile HW3 server.cpp, you need to have those 3.h file. You need to have HW3 server.h, and that's everything you need to compile HW3 server.cpp. Similarly with HW3 client.cpp, you also need a bunch of .h file. So include, which is, you can see the green line is always directing from one .h file to the .cpp file. There's nothing from a CPP file to another CPP file. It's always depend on the .h file. That's the compiler dependency relationship. Okay, so the only thing that's actually going to be different between client and server is that now the client need to depend on the shadowfly.h. Is .h file pointing to a CPP file. And then you have to, the second step, once you actually compile .o file, the red link represent the linking. So now if you want to compile you want to generate the executable HW3 server, you will need all the .o file from core.cpp, person.cpp, transaction.cpp, and HW3 server.cpp. If you want to compile HW3 W3 client, you will need more because now you need shadowfly.cpp as well. And those are the file, which you don't need to worry about that. I showed this to you. This is essentially what the flow of the compilation that the make file is trying to control. And also it tells you how this more than 10 files, they're related to each other and how do you actually get it to run. Okay, so I think we quickly went through the basic idea of a shadow object, and it's a very powerful concept. I show you a working example that you can use this to not only to understand, but use this to develop your own version of homework assignment number 3, part 2, which essentially homework assignment number 2, homework assignment number 3, part 2, I'm sorry, that I asked you to do 3 things. But in the example, I only do 1 thing, the first thing, and you need to finish the other 2. You can modify all of them, and you can even modify the JSON if you want. By the way, you have to modify JSON. I took it back. And you can introduce any new class you want, as long as your system will allow the object be able to communicate with each other as specified at homework H3. Okay? All right, I hope you enjoy and learn from this and start programming. And I will see you tomorrow.